In Lab 2, you need to change the wall model setup to a wall resolved setup, and you also need to be able to change from the SA turbulence model to the K omega SST turbulence model. In the previous videos, we talked about how to change the mesh to have a change between wall model and wall resolved mesh. In this video, we'll talk more about the boundary conditions. First of all, we know that we're dealing with the SA, or using the SA turbulence model by going into constant turbulence properties. And you see that here, Speller-Amara's turbulence model. Let's go into the 0 folder. Remember, we have 4 files: the velocity, the pressure, nu-t, and nu-tilde. The velocity and pressure is a pretty standard setup, so we won't go into those. But remember, the way that turbulence models work is by trying to calculate a turbulent viscosity, nu-t, which is essentially artificial turbulence that gets added into your solution. And depending on the turbulence model that you use, the way that this nu-t, turbulent viscosity, gets calculated is different. Right now we're using the SA turbulence model, which is a 1-equation model. That's why we have another file called nu-tilde, which is a value that gets calculated from the SA turbulence model, and that gets used to determine the turbulent viscosity nu-t. So let's actually take a look at the boundary conditions. Nu-t, the turbulence viscosity. If we look at the boundary conditions, we have our boundaries: sides, inlet, top and bottom, outlet, and wall. The sides are set as empty. The inlet, top and bottom, and the outlet are set to be calculated. They're calculated from the value that is given by nu-tilde. The line underneath here, value, this line is just a placeholder and it actually gets ignored. So the main point is that these get calculated from nu-tilde. At the wall, our demo case is set up to use a wall function. So we have the nu-t u Spalding wall function. Okay, now one of the important things when setting up a turbulence model is setting the initial conditions at the free flow or at the inlet. We haven't talked about this yet. Right now, our inlet is, for the nu-tilde, is set to have some fixed value of 5.84 e to the power of minus 6. This value, depending on this value, the way that nu-tilde gets calculated can be very different. How do we know what value to put in here? Well, we can always go search the documentation and see what value we should use. Go to the documentation, which has all the information about this turbulence model. And if we scroll down a little bit, we see some information about what boundary condition we should use. For the nu-tilde at the far field, which is basically where our inlet would be, it should be set between 3 to 5 times the free stream kinematic viscosity. So there's no fixed value, like one correct value that you can use, but actually a range of values that are suitable for the problem. Let's assume that our free stream velocity nu is equal to 1.5 e to the power of minus 5. That means our nu-tilde at the inlet can be between 7.5 e to the minus 5 and 4.5 e to the minus 5. So some value there will be an appropriate value to set. So let's update this to something in between. Let's say 6.0 e to the minus 5 and also set the internal field to be 6.0 e to the minus 5. For the new t, essentially we can use some value in the range here at the far field. So let's just use 1, and so this will be the same as the free stream kinematic viscosity, 1.5 e to the minus 5. Now let's say we want to change this setup from a wall modeled setup to a wall resolved setup. The only thing we need to change at nu t and nu tilde is the boundary condition at the wall. Right now, nu t and nu tilde are both set up to use the nu tu Spalding wall function. But if we look at the documentation, it says that at the wall, they should be set to 0, which makes sense, because at the wall, there should be no turbulent viscosity. So all we have to do is, instead of using this wall function, we just need to say that we will have a fixed value of 0. Same here, instead of using a wall function, we will use a fixed value of 0. Okay, so now let's say we want to change the turbulence model from the SA turbulence model to the K omega SST turbulence model. The first thing we would need to do is go back to our turbulence properties page and change from this SA to K omega SST. Now let's go back to our 0. We're still trying to calculate the turbulent viscosity nu t, but instead of using the SA1 equation from nu tilde, we're going to have two equations, k that determine k and omega, and use those to calculate nu t. So what I'm going to do is I'm going to make a copy of nu tilde, call this k, and call this omega. So now I have k and omega. And open these. All right. So the first thing we need to do is make sure that we change this omega object to omega. And we also change the dimensions. K is the turbulent kinetic energy, and the dimension for that is like this. And omega is the specific dissipation rate, and the dimension for that is like this. For K, we need to set up the, similar to what we did before, let's find the documentation of the K omega SST. This will help us determine what boundary conditions we should use. For nu tilde, earlier, we had to calculate the value, the boundary condition value at the inlet or the far field. For K and omega, we need to do the same, using these suggested ranges. Now, this is actually quite tedious to calculate, and because the K omega SST turbulence model is so widely used, there are a lot of online calculators that you can use to calculate the values to use. So let's just type k omega SST calculator. And we just need to input some known values of our problem, and it'll give you a reasonable k and omega value you can set for your far field. So I might be wrong, but I think the free stream velocity should be around 18 meters per second. We don't know what the turbulent kinetic energy k is. We don't know what the turbulence dissipation omega is. Turbulence intensity, now this is something that we need to set in order to calculate this. Usually this ranges between 1 and 10%, and in our case we will assume that the turbulence intensity is around 5%. Our length scale, I don't remember exactly, but I think it was around 0.05 meters. And kinematic viscosity, let's leave it as the default setting. Now, based on these values, we want to calculate the turbulence variables. So it seems like for k, this is an appropriate value to use. So we will change the far field value to these. And for omega, it seems like this is an appropriate value to use. So we will change it to these. Now, at the wall, k should be 0. So that's fine. But for omega at the wall, it needs to also be calculated to some value. Now this is because omega is a dissipation rate that is based on the distance between the wall and the centroid of the first cell. That's why you see a delta D term here. Now we could go ahead and manually calculate this, but a more easier way, a roundabout way of doing this is instead of having some fixed value for omega at the wall, we can make use of something called the omega wall function. So although we're doing a wall resolved setting right now, for the omega, we can use the omega wall function to for OpenFOAM to calculate appropriate omega values around the wall for us. And because we're using a wall function at omega, we need to change the nu t from fixed value to using this specific wall function, nu t low Reynolds wall function. This is a special type of wall function that has the same effect as setting the value to 0. But because we're using a wall function at omega, and when you're using a wall function, it needs to be coupled together with other variables, we specify this wall function. Now, if we wanted to change this so that we are using the wall function for the k omega SST model, first of all, at k, we can use the kqr wall function instead of using a fixed value of 0. And at omega, we will keep on using the omega wall function. And for the nu t, instead of using the special wall function, we will use something called nu t u wall function. That is it for all the boundary conditions that you need to change. There's a couple of things you need to change still. That's in the schemes folder, schemes file, and the solution file. In the schemes file, when we're calculating gradients, we have a way to calculate the new tilde. All you have to do is change this to k, and because we also have omega, we add this. Same here, we're not using new tilde anymore, we're using k. And omega. Similarly, if we go into the solution file, solution setup, we're not using new tilde anymore, we're using k and omega, k and omega, k and omega, k and omega, k, omega. Okay. And now you're ready to run it in the k omega SST turbulence model.